Okay, welcome to the EduSat program organized by Department of Technical Education, Karnataka. Today we are discussing about the bending moment and shear force chapter, which is very important chapter related to this strength of materials is concerned. In this chapter mainly we are discussing about the beam, how to draw the bending moment and shear force diagram for the different types of beams. What do you mean by beam? Beam it is very important to know this beam is used for all our civil engineering structures to carry the load. It in many engineering structure members are required to resist the forces that are applied laterally. That is, laterally means perpendicular to the member. These beams will transfer the load to the columns. A structural element which is subjected to load perpendicular to its axis. Here we can observe this is the load which is acting perpendicular to the axis of the beam. This is free from axial forces. There is no axial forces, only transverse forces will act on the beam. And also it is subjected to the bending, shear and deflection. In this strength of materials, we will study how to calculate the bending moment, shear force as well as deflection. These beams, this load will be transferred to the side columns, loads to the columns. Materials used for beam, we can use metal, wood, concrete, plastic, but most commonly used for structural members, metal, concrete. Metal is the steel structures what we are having in I sections, C sections and all, and concrete structures. These are some forms of the geometric forms of the beam sections. Rectangular section, which is most commonly used, and also T section, T beams, I sections, channel sections, this circular sections. These are the most commonly used sections. For designing the beam, we require these following important parameters: reactions, maximum shear force, maximum bending moment, maximum deflection. If we know these parameters, we can design the beam. These beams are classified into cantilever beam, simply supported beam, overhanging beam, fixed beam, continuous beam. Out of which according to our DT syllabus, we are going to discuss in detail cantilever beam, simply supported beam, overhanging beam. What do you mean by cantilever beam? This cantilever beam, you can observe here in this figure, one end is fixed and other end is free. Fixed at one end and other end is free, then it is known as a cantilever beam. These beams where we can see one side is casted inside the column and other end is free. For example, in balcony cantilever position, we can observe beams from the overhanging from the one end. Another one is simply supported beam. Simply supported beam supports at both ends, two sides supported, and if we apply the load, then this type of beam is known as a simply supported beams. Two supports are there. A is one support and B is another support. Overhanging beam. In this type of beam, the two supports, after the two supports, extension was there, that is a cantilever portion. If it is extended one side, it is called as an single overhanging beam. Here we can observe A is the one support, B is the another support, and balance L1 is extending, their point load is applied. Another one is second type of overhanging beam is double overhanging. This side also overhanging, A as well as right side also overhanging, and centrally there are two supports are there. This type of beam is known as a double overhanging beam. Fixed beam. When both ends are fixed, then it is known as a fixed beam. This will be encased in the column. A and as well as B, both the sides are encased inside the column. That type of beam is known as a fixed beam. Then continuous beam. If it is having more than two supports is known as a continuous beam. Here we can observe 1, 2, 3 supports are there. It is continuous over the second support. Next, we have to know what are the different types of loads which acts on the beam. One is concentrated load or point load. The load acting at the point on a beam. For example, here we can observe central one arrow is there, that is vertical load acting at the one particular point. That type of load is known as a concentrated load or point load. We can see example, hanging portion of some light or some weight is hanged on the beam. That type of beam is known as that type of load is known as a point load. Second one is uniformly distributed load. The load spread over the entire length of the beam or a part is known as a uniform load. Here you can see from A to B, beam is simply supported A and B, and 5 kilonewton per meter is acting entire from A to B. That is uniformly distributed. Every meter 5 kilonewton is distributed. If you want to convert this uniformly distributed load into the point load, and what we can do, 5 kilonewton per meter. Every meter 5 kilonewton is acting. 5 into 4. 5 into 4 is 20 kilonewton. 20 kilonewton is acting at central distance. Central distance means 4 meter is the distance between A to B. Center is 4 divided by 2. That means if we want to convert the uniformly distributed load to the point load for calculation purpose, we have to multiply the 5 kilonewton, that is load, intensity of load, multiply with distance, we can get the point load. That point load will act at a distance of half the distance, center distance, that is 4 meter divided by 2 meter distance it is acting from the A, or from B also it is acting 2 meter. We can see examples, uniformly distributed load. See, if it is loaded uniformly like this, some cement bags or load is applied, or even what we can have, self weight of the structure. If it is a weight of the slab, concrete slab, is the uniformly that is a uniformly distributed load. Or if it is a wall is constructed on the beam, that is also uniformly distributed load. Here I have given some examples how to convert the uniformly distributed load to the point load for calculation purpose. This A and B is simply supported, which carries an uniformly distributed load for a distance of 2 meter from the right support. This is the A, B is the right support, A is the left support. This from the right support it is acting at a distance of 2 meter. Then this is the 5 kilonewton per meter is the intensity, multiply with 2, 5 into 2, 10 kilonewton. This 10 kilonewton acts at a distance of half of this 2 meter, center of this 2 meter, that is 2 divided by 1 meter from the B, or here 2 meter plus this half, 2 divided by 2, that is 1 meter, 2 plus 1, 3 meter from the A, or 1 meter from the B. Like this we can convert the uniformly distributed load to the point load, so that we can calculate the bending moment and shear force diagram, shear force calculations. Let us see what do you mean by shear force. So, consider the example here. A, B is the simply supported beam which carries in point loads of W1, W2 and W3. Okay, span of this beam is L, and R1, R2 are the reactions. Reactions means whatever the load is there, W1, W2, W3, that half of that, here it is a symmetrically loaded. If it is a symmetrically loaded, half of the load will be taken by R1 and half of the load will be taken by the R2. If it is not symmetrical, then we have to calculate by taking the moment. Here W1, W2, W3 are load acting, and R1, R2 are the reactions of this AB. Then this if we cut the beam section here, some portion, then here to balance this force we have to apply the Fx, that is the shear force, to balance this, maintain this in the equilibrium. If you want to calculate Fx, this reaction R1, this is upward force minus downward force W1 and W2. Fx is equal to keep an equilibrium, whatever the upward forces must be equal to the downward forces. That is why here if you want to calculate Fx, then R1 minus W1 minus W2, or Fx is equal to R2 minus W3. It can be calculated from right side or from the left side. Therefore what we can say, shear force definition, and also we can abbreviate it as in SF or V. Unbalanced vertical force on one side or one side of the section. It may be left or right of the section, whatever the unbalanced force, that is known as a shear force. The algebraic sum of the vertical forces acting on the body either to the left or right of the section is known as the shear force. If it is the algebraic sum of the right or the left of the forces is known as a shear force. This shear force will tends to develops the cracks in the beam. Then how to calculate the magnitude of to find the magnitude of shear force? Sum of the vertical forces on either side of the section can be determined at any section along the length of the beam. We have to find out the sum of the vertical forces on the left or right of the right section of the beam. Here what we are assuming, downward forces as a positive and upward forces as a negative. Upward forces normally in simply supported beam, it is the reactions, and downward forces are forces acting on the beam. For calculation purpose, we are assuming downward forces as a positive, upward forces as a negative. Therefore, if you want to calculate the shear force is equal to reactions, whatever the reactions we are calculated, minus load to the left of the section. We can calculate from the left side's reaction minus load to the left of section, or reaction at the right side and minus load to the right of the section. Second point is calculating the moment, bending moment. For bending moment purpose, we should know what do you mean by clockwise and anti-clockwise moment. Moment is the product of the force and perpendicular distance between the line of action of the force. If you want to calculate the moment, we have to multiply the load into perpendicular distance. Multiply the load into load and perpendicular distance. Here we can observe there are the two types of moment, clockwise moment and anti-clockwise moment. Clockwise moment, you can observe here, if it is a 25 kilonewton is acting at the right side, if you want to calculate the moment, 25 into distance, that is anti-clockwise moment. It will 25 into distance, that creates an anti-clockwise moment. If it is an 15 kilonewton, if you take 15 kilonewton into distance, 15 kilonewton multiplied by distance, it will create a anti-clockwise moment, and this will create a clockwise moment. Here we can see 50 kilonewton multiplied by 6. If you want to calculate the moment at this point, 50 into 6, that will be clockwise moment. 80 into 4, this will create a anti-clockwise. Okay, clock, it is a clock which direction it moves, that is known as a clockwise moment, which is the opposite direction is known as an anti-clockwise moment. Here we can calculate the moment. Let us say 5 kilonewton is acting at the free end of a cantilever beam. This is the cantilever beam, one end is fixed and other end is free. 5 kilonewton is acting at the free end. 5 kilonewton into distance 3. 5 into 3. 5 into 3 is equal to 15 kilonewton. This is clockwise because 5, if it will tries to turn this beam in this direction, clockwise direction. 5 into 3, 15 kilonewton meter. Its unit is kilonewton meter, which is clockwise moment. Let us take simply supported beam. Here point load is acting at a distance of 2 meter from the A. Moment at A. If you want to calculate the moment at A, here vertical load is 5 kilonewton, downward load is 3 kilonewton, upward load we are taking as a negative, and downward load as an here 5 into 4, which is the anti-clockwise. 3 into 2, which is clockwise. 3 into 2 plus 5 into 4. 3 into 2, what I have taken as a negative. One moment is taken as a negative and another moment is taken as a positive. Clockwise moment is considered as a negative. Anti-clockwise moment is considered as a positive. 3 into 2 plus 5 into 4. See, it is clockwise and it is anti-clockwise. Second one is total moment is 14 kilonewton meter. Similarly, we can consider the UDL, uniformly distributed load, which is acting at a 5 kilonewton for entire length 4 meter. To calculate the moment at A, we have to convert the 5 kilonewton per meter into the point load. 5 into 4 is the 20 kilonewton, which acts at a distance of 2 meter from the A or 2 meter from the B. Okay, if we divide this 4 divided by 2 meter, therefore we can make a simplified diagram of uniformly distributed as in concentrated load. Then we can calculate the moment. Moment at A is equal to minus 5 into 4. 5 is the downward load, 5 this is clockwise moment, 5 into 4 is the 20 kilonewton which is acting, and clockwise distance is 2 meter. 20 into 2, that is the load, 20 is the total load, into distance is 2 meter, 4 divided by 2 means 2 meter, plus 10 into, this is the vertical load, 10 into this distance, total distance is 4 meter, 10 into 4, that we will get the moment. If you see here 5 into 4 plus into 4 by 2 plus 10 into 4, that is the moment about the A. Therefore, what we can get, moment at A is equal to 0. Next, bending moment. Now we know the moment. Moment is the force into distance. This bending moment will cause us when load is applied on the beam. Okay, this is bending moment is generally denoted by M or BM. Okay, this bending moment tries to bend the beam. Definition of bending moment is algebraic sum of the moment of all the forces acting on the beam either to the left or right of the section is known as the bending moment at a section. Similar same way, algebraic we have to sum the all the moments about the any one particular point, left or right, then whatever the value we will get, that is known as a bending moment. We are using in some conventions for a bending moment calculation, same way how we are consider the upward and downward forces in shear force calculation. The bending moment is considered as a sagging bending moment if it tends to bend the beam to a curvature having convexity at the bottom as shown in figure. Here we can see the figure. If it is a beam is bending like this, then it is known as a sagging bending moment. It is sagging. Okay, this sagging bending moment also called as a positive bending moment. Sagging bending moment generally we will observe in the case of a simply supported beam. Here if it is a load is applied for the simply supported beam, then it will bend like this. Normally this simply supported beam undergoes the sagging bending moment. Second type of bending moment is hogging bending moment. If it is a convexity upward is known as a hogging bending moment. This is also known as a negative bending moment. Hogging bending moment is observed in the cantilever beam. When cantilever beam is loaded on the free end, it will bend like this. Therefore, upper portion will be under the tension and bottom portion will be compression. This type of a beam, this cantilever beam will undergo the hogging bending moment. Magnitude of bending moment. Magnitude of bending moment, what we can consider as in moments of reactions minus, first we have to calculate the moment of reactions minus moment of the load to the left of the section, or moment of the reactions minus moment of the loads to the right of the section. We can calculate the bending moment from the right side or we can calculate from the left. First we have to take the moment of the reactions, then from that we have to minus the whatever the loads acting into distance to the point where we needed the bending moment. After calculating the bending moment and shear force, we have to draw the shear force diagram as well as bending moment diagram. The shear force diagram shows the variation of shear force along the length of the beam, whereas bending moment shows the variation of the bending moment along the length of the beam. From that we can observe where bending moment is and shear force is maximum and minimum. According to that we can design the beam. Why we need the shear force diagram and bending moment diagram? It is used to determine the size of type of the beam or size of the beam and which material we have to use for the constructing the beam. And also another application of shear force and bending moment is to know the deflection. What is the extent of beam deflects under the load. Let us see how to calculate the bending moment and shear force for the cantilever beam. I have considered this cantilever beam fixed at A and free at the B point, and it is carrying an point load of W. To calculate the bending moment and shear force at the important point, salient point means here I am considering the point A, B and point A. Point A is the fixed and point B is free end. Let us what is the definition of shear force? Whatever the unbalanced force acting on the right or left of the section. Shear force at B. First is shear force at B. What is the shear force at B? Load is acting at W. We will write it as an W plus. Plus means downward force is considered as an positive. Here unbalanced force at the section B is plus W. Next we will move on to the A point. A point, up to A point, whatever the right of the section, from A right of the section, whatever the balanced unbalanced force is W only. If it is any further load is added, then it is added to this W. Now no further load is added, therefore shear force at A also W. To draw the shear force diagram, what we can see, first you have to draw the horizontal line, and then whatever the value W, we have to draw the W value at A as well as the B, and then if you join, then we will get the rectangular shear force diagram, which is positive, because both the values W is plus plus, that is why it is considered as a positive shear force diagram. Then to draw the bending moment diagram, bending moment means force into distance. For point B, we have the force exactly point acting at the point B, distance is 0, force W into distance is 0, therefore bending moment at B is equal to 0. Then bending moment at B, A, force into distance, force is W, distance is L, force into distance means W into L. Bending moment at A is W into L, bending moment at B is 0. Therefore, if we draw the bending moment diagram, it is a triangular shape with having a maximum bending moment at the A and 0 at the B. What we can observe here, maximum bending moment occurs at the fixed end, minimum bending moment occurs at the free end. Similarly, shear force is maximum at fixed end, as well as what we can observe, shear force is also W at the free end also. Next, cantilever beam carrying an uniformly distributed load. Here, if you want to calculate the shear force and bending moment for the uniformly distributed load, we can convert this uniformly distributed load to the point load, or when calculating itself, we can multiply the length, distance with the load. Shear force at B. At B point, shear force, no load is acting, therefore shear force at B is equal to 0. Shear force at A, W is the load acting per meter into distance is L. Total load acting from A to B is W into L, WL. Shear force at A is WL. Similarly, bending moment at B, force into distance is 0, bending moment at B is equal to 0, bending moment at A, force into distance, W into distance is L, W into L, W into L into L by 2. It is acting at a distance of L by 2. L is the distance divided by 2. This point, this uniformly distributed load acts at the center. From the center, distance is L by 2. W into L by 2. If we multiply L into L square, WL square by 2. WL square by 2 is the maximum bending moment, and bending moment at B is 0, bending moment at A is WL square by 2. This is while drawing the shear force and bending moment diagram, we can observe here shear force at B is 0, we can put in point and then draw a horizontal line. Shear force at B is W into L, WL, then if we join, it will be triangle. Whereas this bending moment diagram, at B is 0, at A is maximum WL square by 2, and we have to join A to B by parabolic. We have to draw the parabolic, it is not a straight line. when we are calculating the bending moment and shear force, we can observe how we have to draw the complete diagram. Next, simply supported beam carrying a central point load. Third case, simply supported beam A and B is simply supported and it is carrying in central point load W. First, for cantilever beam, reaction is not required to calculate, whereas in simply supported beam we have to calculate the reactions A and B. To calculate the reaction, since this is symmetrical, this load is exactly acting at the central point L by 2, we can calculate the RA and RB by dividing the W, half of the W by 2 RA and W by 2 RB. Okay. W by 2 is the reaction at A as well as reaction at B. After calculating the reaction, then to start with shear force at B, W by 2 is the acting at the upward direction. Upward force is considered as an positive, downward force is considered as an, the upward force is considered as a negative, downward force is positive. Here we are taken minus W by 2 is the load acting at the B, that is shear force at B. Next, shear force at A. Shear force at A, again what we can observe, W by 2. It is the, if we add W by 2 minus W by 2 plus W, we will get W by 2. That is the shear force at the A. Bending moment at B. Bending moment at B is 0 because force into distance is 0. Bending moment at C. C is the center point. If we want to calculate the bending moment at C, we have to multiply the force RA RB into distance L by 2. RB into L by 2. RB is W by 2 into distance is L by 2. We will get WL by 4. WL by 4 is the bending moment at C. Bending moment at A will be 0. You should observe that if you calculate the moment from RB into L minus W into L by 2, we will get the 0 at the A. That means simply supported beam, bending moment at A as well as bending moment B will be 0. And central point, what we can observe, it is maximum, WL by 4. Bending moment at center is maximum, bending moment at ends is 0. Whereas shear force at center is 0, shear force at the support is maximum. To draw the shear force diagram, here we can see minus W by 2, here down, horizontal line below it is there, W by 2 at shear force at A, W by 2 which is above. Therefore plus and minus, both shear force changes its sign at the center point. That is why where shear force changes its sign, that point we will get the maximum bending moment. Maximum bending moment occurs where shear force changes its sign, or shear force is equal to 0. Next, simply supported beam carrying an uniformly distributed load. In this case, we are consider the A and B as a point, and it is carrying an uniformly distributed load entire span. To calculate RA and RB, what is the total load acting? W is the load into distance is the L. WL is the total load acting. Since it is symmetrically loaded, we can divide the total load to 2, divide by 2, W into L divided by 2, we will get the RA at A. RA is WL by 2, here RB also WL by 2. Half of the load, total load is W into L, and divided by 2 is the half the load. RA carries in half load and RB carries in half of the total load. Then to start with the shear force at B, shear force at B is WL by 2 minus WL by 2. Since it is a upward force, minus WL by 2 is taken. Shear force at A also WL by 2. When you add the minus WL by 2 plus W into L into W into L is the total load. W minus WL by 2 plus WL if you add, then we will get the RA as an WL by 2. Similar case what we did in the previous simply supported point load. Bending moment at B also 0. Bending moment at C, at central point, C is the center point. To calculate center point bending moment, first we have to multiply RB into L by 2. Center point is L by 2, RB into L by 2, which is the, anti-clockwise movement, that is why it is considered as n plus, minus W into load. Load is W is the load, which is we are taking only half of the load. W into L by 2 is the half. L by 2 is it is acting at a distance of L by 2 only. We are considering a half load into L by 4. L by 4 means this half of the portion of the load will act at a center. Center means L by 2 is the load acting. Half of that center is L by 4. L by 2 into L by that is L by 2 is the half into half, that is L by 4. W into L by 2 into L by 4. Therefore, if we simplify this, we will get WL square by 8 is the moment at the C. What we can observe, maximum bending moment is WL square by 2 and bending moment at A and B is 0. We have to mark a draw a horizontal line, and A point to B point we have to draw the parabolic curve. For shear force diagram, we can observe one horizontal line, then this WL by 2 is the shear force at the B point and WL by 2 is shear force at the A point. Here minus sign because it is a downward minus and this upward. Then if we join this, we will get a triangles. Shear force diagram will be having a straight line, inclined line. Wherever the uniformly distributed load occurs, there we have to draw the inclined line. When load is there, we have to draw the vertical line. Whereas in bending moment diagram, when uniformly distributed load occurs, then we have to draw the parabolic line. If it is an point load, that is inclined lines. Then bending moment at A is equal to 0. These are the four cases what we have discussed now. Simply supported beam, point load at center, reaction is W by 2, W by 2. Shear force diagram will be like this, two rectangles, and bending moment diagram is triangle with the maximum bending moment WL by 4 occurs at the center. Then uniformly distributed load, simply supported beam carrying an uniformly distributed load of entire length, WL by 2, WL by 2 is the half of the load, reactions, and then this is the shear force diagram which consists of two triangles, and then this bending moment diagram will be WL square by 8 at the center. It is a parabolic. Maximum bending moment is WL square by 8. For cantilever beam, if it is carrying a point load, it will be shear force diagram will be rectangle, bending moment diagram will be triangle with maximum bending moment WL. Then uniformly distributed load for cantilever beam, its shear force diagram will be triangle and bending moment diagram which consists of a parabolic with maximum bending moment WL square by 2. These are the four standard cases what we discussed. What are the important points what we observed? We can consider the left or right portion of the section when we are calculating the bending moment or shear force. Add the forces including reaction normal to the beam on one of the portion. If right portion of the section is chosen, a force on the right portion acting downwards is positive, while the force on the right portion acting upwards is negative. That is, if we consider the right portion, then downward we can consider as a positive and upward as a negative. If the left portion is considered, then a force on the left portion acting towards this positive, while force on the left portion acting downward is negative. We have to take a reverse case when we consider the left portion. The sign should be considered reverse. Then whenever a concentrated load is acting, including support reactions, if it is a concentrated load is acting, then shear force will suddenly change. Wherever the point where concentrated load is acting, that point shear force changes, suddenly changes. The change is numerically equal to the load. Whatever the load value, if it is a 10 kilonewton is acting at one particular point, then the shear force value will also 10 kilonewton, which is vertical drop. Then if there is a no load, if it is any no load is there, then the shear force will be horizontal. Shear force diagram will be horizontal line. The shear force diagram consists of a rectangles in case of point loads and inclined lines for the portion of a UDL. If it is an point load, then shear force diagram will be rectangles. If it is an uniformly distributed load, it will be inclined lines. Then bending moment is 0 at supports of a simply supported beam. If it is a simply supported beam, then bending moment will be 0 at the support, what we observed when we are calculating. Bending moment is 0 at the free end for cantilever beam and maximum at the fixed end. And also we should note down that bending moment is 0 at the free end for cantilever beam and also maximum at the fixed end. Maximum bending moment occurs wherever shear force changes its sign. Where shear force changes its sign, that point maximum bending moment occurs. The bending moment diagram consists of inclined lines in case of point loads and parabolic curves for the portion of the UDL. Now, that also we have observed. Bending moment we have to draw the inclined lines if it is in point loads. If it is an uniformly distributed load, we have to draw the parabolic curve. Next, shear force and bending moment are to be calculated at various sections of the beam to draw the shear force and bending moment diagram. We have to note down the salient points. From that points we have to calculate the shear force and bending moment diagram. These sections are generally considered on the beam where the magnitude of the shear force and bending moments are changing abruptly. That means wherever the loads, point loads are there, and at the ends of the bending moment, this uniformly distributed loads, that points and supports, we have to calculate the bending moment and shear force. Let us take one simple example to understand the bending moment and shear force calculation. This is the cantilever beam carrying in 3 kilonewton at a distance of 2 meter from the support, 5 kilonewton at a distance of 4 meter from the support, 8 kilonewton at a distance of 6 meter from the fixed end. Okay, 3, 5 and 8 kilonewton, 3 point loads are acting. Let us mark and point as an A, B, C, D are the salient points. Wherever the point loads are acting, that points we have to calculate the bending moment and shear force as well as at the free end and fixed end. For calculating the shear force at D is equal to 8 kilonewton. How it is 8 kilonewton? Here from right side D point 8 kilonewton only one load is acting, that is we have to write down. This is downward, that is why it is a positive. Then shear force at C point, up to C point, whatever the forces are acting, that we have to consider. 8 kilonewton is already considered, plus 5 kilonewton is added. 8 plus 5 is 13 kilonewton. Next, shear force at B. At B, already we are calculated 8 kilonewton plus 5 kilonewton, that is 13. For that another additional load added, that is 3 kilonewton. 13 plus 3, 16 kilonewton is shear force at the B. That means whatever the algebraic sum of the forces, unbalanced forces at right or left of the section. Now I am considering this right side section, whatever the load is acting. Next move towards the A. Shear force at A, this 8 kilonewton plus 5 kilonewton 13 plus 3 16 plus any other load is there. No load is there, therefore total shear force is 16 kilonewton. To draw the shear force diagram, first draw the horizontal line and then starting point, first D point, we have the 8 kilonewton upward, and also you can observe this vertical line is equal to the 8 kilonewton. 8 kilonewton whatever is there, that is the vertical line here. Shear force value will be equal to this vertical point load 8 kilonewton. Then from D to C there is no load is there from C to D, therefore we have to draw the horizontal line. Shear force diagram will be horizontal line if it is no load is between the two loads. If load is there, then it will be vertical line. Next at C we have draw the 5 kilonewton extra, that is 8 plus another 5 is added. 5 kilonewton drop is there at the C. 8 plus 5, total shear force at C is 13, but there is a drop of equal to the point load 5 kilonewton. Then again from C to B there is no load is added, therefore it is a horizontal line. Then again that 13 kilonewton, 3 kilonewton is added. That 3 kilonewton drop is equal to the vertical point load. From B to A no further load is added, therefore horizontal line. This is the shear force diagram. Wherever the point load is there, that plus equal to that point load, we have to show the drop. Wherever load is not there, we have to draw the horizontal line. Then bending moment calculation. Bending moment at D, force into distance. Distance is 0, therefore bending moment at D is equal to 0. Bending moment at C, force is 8 kilonewton is acting. 8 kilonewton into distance is 2 meter. 2 meter is the distance from the D to C. 8 into 2, 16 kilonewton meter is the bending moment at C. To calculate bending moment at B, force is 8 kilonewton into distance is 4. Force into distance 8 into 4 plus 5 into 2. 5 into distance is 2 meter. 8 into 4 meter. 5 into 2 meter. We have to calculate force into distance for moment. 5 into 2, 8 into 4. 8 into 4 plus 5 into 2, total 42 kilonewton meter is the bending moment at B. To calculate bending moment at A, force is 8 kilonewton into distance is 2 plus 2 plus 2, 6. Total 6. Distance from 8 kilonewton to A point is 6 kilonewton. 8 into 6 plus 5 kilonewton into distance is 4. 5 into 4 plus 3 kilonewton into distance is 2. All the loads into distance to point where we require the bending moment. A means A point, we have to multiply with 3 into distance, 5 into distance, 8 into distance. If it is B, 5 into distance, 8 into distance, 5 into distance. If it is C, only 8 into distance, this C. Okay, like this we have to calculate the bending moment diagram at each point where point load is acting as well as the support sections. Here bending moment at A is 74 kilonewton. To draw the bending moment diagram, first draw the horizontal line. All this bending moment is, then draw the one vertical line 74 kilonewton, which is the maximum bending moment, and then join each point equal to its bending moment value 16 kilonewton, 42 kilonewton by straight lines. Since it is a point loads, we have to draw by the straight lines. If it is an UDL, then it is a parabolic. Okay, all negative because it is a sagging bending moment. Okay, so what we discussed today, a structural element which is subjected to loads transferred to its axis is known as a beam. That is first point. We discussed about the definition of beam. A beam with both of its ends on simply support is known as a simply supported beam. If beam is both ends is supported, simply supported beam. The supports exertion reaction. We have observed whenever if we want to calculate the bending moment or shear force diagram, we should calculate the support reactions for the simply supported beam. A beam with one end fixed and other end free is called the cantilever beam. Second one is cantilever beam, which is fixed at one end and free at the other end is known as a cantilever beam. There is a vertical reaction and movement at the fixed end. Shear force is unbalanced vertical force on one side to the left or right of the section of the beam and is sum of all the normal forces on the one side of the section. Shear force is the unbalanced force acting on the right side or the left side of the section. Shear force is considered positive when the resultant of the forces to the left of the section is upward or to the right downwards. Then a shear force diagram shows the variation of the shear force along the length of a beam. The shear force shows the variation, whereas bending moment shows the variation of the bending moment. Bending moment at a section of a beam is algebraic sum of the moment about the section of all the forces on one side of the section. Similarly, bending moment also, if we want to calculate, we have to calculate algebraic sum of the moment at the right or left of the section. The bending moment causing the concavity upward is referred to as a sagging bending moment and is taken as in positive. Sagging bending moment is taken as in positive. A bending moment causing in convexity upward is taken as a negative. It is called the hogging bending moment. A sagging bending moment occurs in the simply supported beam. Hogging bending moment occurs in the cantilever beam. A bending moment diagram shows the variation of bending moment along the length of the beam. Thank you. Next class we will discuss some more problems.